Okay, before we get into the lesson itself, let's look at these two warm-up problems from beforehand. Okay, number one says we have a graph, negative 1/6 x minus 4. Right, so some things about the graph. We have a slope of negative 1/6, right? That's this part. This is the slope. And this is your y-intercept, so it crosses your y-axis at negative 4. Some information about that is probably not too important for this problem. It says which ordered pair is in the solution set of y is greater than this line. So we want all the y values that are greater than whatever that x value happens to be. So number one, what happens to that line if it's a greater than symbol? What type of a line is greater than or less than? A dashed or a dotted line. Right? So number one, we're going to change this line to be a dashed line since it says strictly greater than. And then number two, what side do we shade if it is greater than? Above. All the y values that are greater than are up here in this area. So we're looking for any point that is in this shaded area. So which one is that point? I'm just going to go ahead and say it's probably going to be, which one is it? That's a good question. Negative 8, 8, negative 8, 8 is up here. Well, that's clearly in the solution set. I don't think we need to go any further than that. Negative 8, comma 8 is well above that dashed red line. So that's going to be in the solution set. All those other ones are not. Okay, so a reminder about that. And then number two from last week, the expression is equivalent to x to some n. So we want to simplify this to figure out what is the exponent, right? What is the exponent from our final answer? That's what we are looking for. So PEMDAS, right, parentheses, please excuse my dear Aunt Sally, says we have to first do this. We have to do this one because it's a power raised to a power, right? Power raised to a power. We want to get rid of that parenthesis first. So nothing changes on this one. This is still x to the minus 8. But this one becomes x to the 2 times 3. When we have a power raised to a power, we're going to multiply those powers together. 2 times 3 is 6. So now that we have simplified our x squared to the third power, now we can do this operation. And what is the operation that happens between these things when we are multiplying their x's together? That operation is addition. So we're going to add these two things together. Okay, adding the exponents. When we have two letters, we are adding the exponents. So negative 8 plus 6 is negative 2. Okay, and that's really what we're being asked for. What is the exponent when you simplify this down? The exponent is negative 2. So if we want to write it in an explicit manner, we would say n, since that's the question. What is the value of n? N is negative 2. Okay, now if we were going to simplify this further, we would take this negative exponent and put it in the denominator to become a positive. Right? So if we were going to be simplifying this, if it was a different question, then your final answer would look like this. 1 over x squared would be the simplified version of our answer. But the n value is negative 2, because that's what it asks for. Okay, so that's what we did last week. Questions like number 2 will be on your test on Friday, but I don't think any like question number 1. But I'll make sure to look and tell you tomorrow. Okay? So today's real lesson is about simplifying radicals. So this thing here, this is called a radical expression. Okay, because it has this symbol in it. It has what's called a radical. Okay, I wasn't around when they were naming these things, but this symbol is the radical. That's the radical sign, sometimes called the square root. okay, but it's really called a radical. Okay. The radicand is the number underneath your radical. So whatever is underneath your radical, in this case, the radicand is 5. That is called your radicand. So the symbol or the sign is your radical. The thing underneath it is called your radicand. And then your index, well, that's the only thing we have left here is what goes in what I call the elbow. Right, it's the, I don't know, the crook of your symbol there, the radical elbow. I don't know, wherever you want to call it, right, that's called the index. When we don't see an index, right, if it's just this symbol, then we can understand that the index is 2, or the square root, the second root. Okay, that's what we do a lot in math, is we take the square root of things if we're solving a square. But you don't really see a square. If it's just that symbol without an index, you can assume that the index is going to be a 2. Okay, but because it happens so often, mathematicians don't write the 2 there because they want to be efficient. And they said, well, that's fine. That's called the square root. Right? If no index is shown, it is a 2, which makes it the square root. Oh, we just said that right there. A 2. Square root. Okay, simplifying square roots of perfect squares. Okay, when they're perfect squares, we have an index of 2, the second power. Right, to undo an x squared, we would raise it to the second power. Okay, so simplify. What is the square root of 9? What number times itself is 9, right? That's what we're asking for when you have a square root. Is there a number that when multiplied by itself gives you 9? 3, right? 3 times 3. So what we're going to do is we're going to write this as the square root of 3 times 3. Okay, so we're going to break your number into its products, right? Into its factors. And anytime we have a factor pair, that pair will contribute one number to come outside of your radical. Okay, so both of these together contribute one number to come outside of your radical. So the square root of 9 is 3. Okay, how about 2 times the square root of 25? Okay, so when we don't see a symbol here, you are to assume or understand that it is a multiplication problem. We are going to multiply 2, the number on the outside, times whatever the square root of 25 is. Okay? So what is the square root of 25? In other words, what number times itself is 25? What number times itself is 25? That number is 5. The square root of 25 is the real number 5. So then your answer is, what is 2 times 5? 10. The answer is 10. So 2 times the square root of 25 is the same as 2 times 5, which is 10. Okay, so when we don't see an operation symbol, right? There's no plus, there's no minus, there's no divided by. If you don't see an operation symbol, you are to understand that it is a times or a multiply symbol. Okay, negative 5 times whatever the square root of 81 is. So once again, what number times itself is 81? That's our question, right? And these ones are getting larger, so it might be less obvious. The square root of 81 is 9. Okay, the square root of 81 is 9. 9 times 9 is 81. So then what is negative 5 times positive 9? And our calculator says negative 45. Okay, so the final simplified answer for this problem is negative 45. So if we have a perfect square, right? So these are your perfect squares. every number when multiplied by itself. So what's 1 squared? 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared, 49. Right? These are all of your perfect squares. We're going to go up to 10 squared. 64 is 8 squared. 9 squared is 81. And 10 squared is 100. So all the numbers on the right are called your perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Those are all perfect squares because they come from one number multiplied by itself. Okay, so here are some using what's called prime factorization trees. Okay, prime factorization trees. The first thing you want to do is just choose two numbers that multiply to give you whatever is underneath your radical. Okay, and then we're looking for factor pairs. Every time we have a factor pair, how many is a pair? 2. We're looking for 2 of the same number, 2 of the same multiplier. You can pull one of those out. Okay, and then anything that's not paired stays underneath your radical. So let's go. It's 32. What numbers off the top of your head multiply to give you 32? What's that? 4 times 7, close. 4 times 7 is 28. 4 times 8. 4 times 8 gives you 32. 32 is 4 times 8. Okay, can we split 4 down into factors? What numbers multiply to give you 4? 2 and 2, right? 2 of them. 2 times 2. And what numbers multiply to give you 8? 2 times 4. Okay, so we have 2, 2, 2, and a 4. So now we can think what numbers multiply to give you 4, right? Because 4 is not a prime number yet. What numbers multiply to give you 4? 2 and 2. Okay, so this is called a prime factor tree. Every one of these numbers, 2, 2, 2, 2, 2, those are all prime numbers, as in their only multiplier is 1 and itself. Okay, so 4 is not a prime number, right? 5, 7, 11, right? Those are prime numbers that we're looking for. So let's box our pair. So here we have one pair of 2's. And where do we have another pair of 2's? Right, the bottom ones. But it doesn't really, because you could pair these two if you want. That's fine, right? That is a pair of 2's. You could pair these ones if you want. That is a pair of 2's. Right? You could pair these ones if you want. That is a pair of 2's. Okay, it doesn't matter what pair you pick, as long as you have circled them or boxed them. Because every time we have a pair, this contributes one number on the outside of your radical. Okay, this contributes one number on the outside of your radical. Okay, every pair contributes one number on the outside of the radical. And now, do we have anything that's not paired? This number here, anything that's not paired stays underneath your radical. Okay, anything not paired stays underneath your radical. So finally, on the outside, what is 2 times 2? That is 4, and on the underside, we just have root 2. Okay, so this is the simplified version of the square root of 32. That is going to be your answer. Okay, making prime factor trees. Prime factor trees. Okay, 50. What numbers multiply to give us 50? What's that? 10 and 5. Those are two excellent numbers that multiply to give you 50. So we split this, right? The tree is the arrow part, like the branches of a tree. We split 50 into its multipliers, 10 times 5. Okay? Can we split 10 anymore? What numbers multiply to give us 10? 5 times 2. Okay, can we split 5 anymore? No, that's just 5 and 1, right? So that is a prime number. So our prime factorization is 5 and 2 and 5. So let's circle our pair. There's a 5 on the left factor tree, and there's a 5 on the right. So we circle the pair, and that contributes 1, 5 to the outside of your radical, right? That's a real number 5. No longer is it a square-rooted number. And anything that's not paired, so the 2 is not have a pair, that stays underneath your radical. Okay, that stays under the square root. So this is the simplified expression for the square root of 50. 5 times the square root of 2. Okay, how about root 15? What numbers multiply to give you root 15? 3 and 5. Okay, can we split 3 into any more factors? No, just 3 and 1. Can we split 5 into any more factors? No, we can't. Which means that root 15 is not simplifiable. So the answer is just root 15. Right? There are no pairs that multiply in here. It's fiable. Not simplifiable. Okay, so if you do it, get it down to its factors, right, to its prime factorization, and you don't have any pairs, that means the original was not simplifiable. Okay, not able to be simplified. Okay, let's look at the back side. What do you say? Sure. So these ones have a multiplier that we're going to multiply by however we simplify root 18. So remember, the 3 is always going to be on the outside of our radical. We won't multiply by 3 until the very, very end. Okay, so let's look at 18. What numbers multiply to give you 18? Okay, and then 2 is good. 2 is a prime number. What about numbers that multiply to give you 9? 3 and 3. So now we have your prime factorization. 3 and 3 and 2 are all prime numbers. So we circle the pair. And that contributes a 3 on the outside of your radical. Okay. We put the 2 back underneath the radical. Okay, 2 does not have a pair, so it stays underneath the radical. And now we still have to deal with this 3 on the outside. Right, remember, there's not an operation between the 3 and the radical, so we need to remember or understand that that is a multiplication. So this 3 on the outside was there in the beginning. So our final answer, what is 3 times 3? 9. So our final answer is 9 root 2. Okay, here we have 28. So 28 is our radical that we're trying to split up. There's a couple ways to split this up. How about 2 and 14? Right, 28 is an even number. Every even number is divisible by 2. 14 is also an even number, so 7 and 2, and then those are your primes. Okay, so we have a pair of 2's. That gives me a 2 on the outside of my radical. My 7 stays underneath the radical, and I still have to remember my negative 2 multiplier on the outside. So the final answer will be negative 4 times the square root of 7. Okay, and then similarly for 54, right? 54 is a pretty big number. I know for sure that it's an even number, so that means it's divisible by 2. And if I divide 54 by 2, I believe I get 27. Okay, now 27 is not an even number, so it's not divisible by 2, but it is divisible by 3. 27 is 3 times 9. All right, I know that one. And then 9 is 3 times 3. Okay, so my prime numbers are the 2 here, the 3 there, and then these 2 3s. Those are my prime factorizations. So I'm looking for the pairs. How many pairs of 3s do you see? There's one pair of 3s, and then you have an extra one. Right? So this pair of 3s gives you 1 3 on the outside of your radical. So this is the first time that we've had two numbers that didn't have pairs. So the 2 doesn't have a pair first, and that third 3 doesn't have a pair either. So both of those numbers stay underneath your radical, and we multiply them together always. And I still have my 4 on the outside, so let's bring that into the picture also. So 4 times 3, and then underneath your radical. So 4 times 3, that is 12 on the outside, and then 2 times 3 is 6 on the inside. Okay, so on occasion you're going to have some multiple numbers that don't have pairs, and we multiply them back underneath your radical, just like you multiply the numbers outside of your radical. Okay, so these are simplifying radicals. Your answer should always have a root in it to end with.